Hi everyone. This tutorial and demo is to follow the tutorial number 1, and in this tutorial we will instead of having the circuit with a resistive load, we had a resistor here in the circuit basically, we're going to use a inductive load, and an inductive load would be a motor, for instance. And this is about a half horsepower induction motor, and it's not very large or anything like that, but it will suit its purpose for this demonstration. Right now the circuit is not connected, and let me go over a bit what is involved here. We have a relay here that we can activate with this battery to just activate the coil to flip between two contact points. The common contact is attached to the induction motor there, and one side of the contact, the normally closed contact side, is attached to the circuit, and the one that is activated by the relay is attached to the grid there. That's because when you have a capacitive series capacitive circuit functioning on this motor, you have to start it on the grid first to get it going, and then so it's just a momentary, for a fraction of a second there, to get it spinning, and then it'll take on from there. So this meter is still here, but just going to display basically their voltage across our motor coil, and all I need to do now is to connect this induction motor to the grid. And now you heard the motor start, and I have a tachometer here that we can get a reading of RPM. So as you see, we're just under 1,800 RPM. And we have 118 volts across our motor coil, and this is just straight from the grid now. We're not looking at adding capacitance yet. And if we look at our data here on the oscilloscope, we can see we have 120 volts from our input from the grid, and we have 6.5 volts going across our 0.1 ohm resistor, and with that resistor we're capable of seeing what's happening between our current here is out of phase with our voltage. And this is a typical inductive load where the voltage will be ahead, and so the voltage is leading, in this case, the current, because the voltage charges in an inductor or a coil before the current does. Current is lagging. And since it is an inductive load, it becomes reactive, meaning that part of it is also returned to the grid, and that is a normal characteristic of a motor, and that's why under AC conditions we need to figure out what the power factor is of our circuit, and power factor will be measured by the phase difference here between the voltage and current. In our previous tutorial we had the voltage and current in phase, exactly over on top of each other, meaning is non-reactive, and the power factor is 1. So basically voltage times current gives us the amount of watts. And in this one, no, in an inductive load or a capacitive circuit, you would have a phase shift, and then you have to determine the amount of degrees you have between current and voltage to get your total amount of power. Now this oscilloscope has that wonderful feature that it can do that math for you, and this is what it's doing right now. So we don't even have to do our calculations, the scope will do it all for us. And this motor, as it's working right now, is using 257 watts, and that's what it's here on the upper end of the consumption of power, and there is the return portion. So this is the performance of the motor as is. So now the only change that I will do is add 35 microfarad of capacitance and put that in series in the circuit. So I'm breaking this apart and putting the capacitor in between, and that's the only change that I'll do, and we will look at that next. Okay, so now I have the 35 microfarad in series with the circuit, so going basically just across there on the hot side, and there's no other changes to the circuit. And the circuit is functioning at this time, but the motor is not capable of turning on its own just under reactive power. Right now the motor coil has only 7.5 volts across it, and this is what it looks like in this condition here. So basically we will have to kickstart it off of the grid temporarily, and it'll maintain itself after that small quick initial start. So here I am going to apply the relay to get it started, and now it is started, and let's here bring up our current so we can get some data there. So the conditions are very different now, and what we can see is instead of using consumption of 250 watts, the motor is now returning 3.7 watts back to the grid, and there's our maximum and minimum that actually reflect that. And you can obviously see now this is the return portion here. This is the use portion. So again, our return portion is higher than our use portion, and our math is capable of calculating the watts based on that. And now if you look at our position of our current, it is 90 degrees out of phase from our voltage, and that's the ideal condition that you would want. And now if you look at what we have on our motor coil, we have about 52 volts going across our motor coil. The motor is turning, and I will give you a display of its RPM. So basically the same RPM, and there you go. The motor is turning itself on reactive power. Now if I apply a load to the motor by putting my finger on here, I will show you what happens to the motor coil. The motor coil reduces in voltage, and if you look at the math, I'm now applying a load, and now you see the scenario change. Instead of it taking returning power, it is now taking power, and the more load I apply, the more now it's starting to take. So now we're using 5 watts instead of returning 4 or 5 watts with this load of my finger on the on that spindle. I let it go, and it returns back to returning power. So the next thing that we'll do is we will connect this to the generator and see that we can actually get this motor to turn off that alternator without it asking for any more current, just like we were doing with the resistive load. So let's pull this out here from the grid. Obviously our motor is stopping there. It stopped, and we will connect this in the generator there, and the generator off, and we will start our generator and look at our power. So we sit usually around 157 watts in average, so maybe 156 at this time. And we'll switch on the circuit, which is the inductive motor, And as you see now, it's gone the other way around, but that's because the motor hasn't been started, nothing's happening. This is our scope shot. No activity. We only have 7.5 volts across our motor coil, so obviously it's not going to start. So now I will kick-start it with the relay here off the grid, and let's have a look and see what happens here. So there it is, taking off on its own, and now it is working off of the generator, and it's not, you know, we only have about 111 volts, so the conditions are not the same as with the grid, because my generator is not capable of powering enough voltage like the grid is, because my induction motor is turning it at 3,500 RPM when it needs to be turned at 3,600 RPM. But we are getting this motor to turn, and we'll take a tachometer reading off of that. So we are pretty close to being same range, just a little lower in RPM. But what is important here is, if you look at our meter, we are still, the motor's on, and we are still within our watt range of it just idling and turning that alternator head. And now I will stop. Well, you can see that it's turning. And now I'll just stop it, and you'll see what the difference is. So maybe it's taking an extra 2 or 3 watts, but that would be all that it is utilizing to turn the motor. But let's stop this now. But in these conditions, what I can tell you is you don't have very much mechanical power at the shaft. I could have stopped it very easily with my finger, with one finger, in the conditions of it operating off of the alternator here. And when it's operating off the grid, a little bit higher voltage, it has a little bit more torque. Now, what the important thing here I'd like to demonstrate now is we will now connect it to 240 volts, basically double the voltage, and we will see the effect of that. Okay, so now I've just basically disconnected my neutral here of the grid, and we're just having our hot here, and the other hot wire will be coming from another side of the panel and combining each 120 volts, so that's now attached where the neutral was. So we have 2 hots of 120 volts, which will give us a total of 240 volts, and when I connect that there, that will complete the circuit. So right now it's not connected, nothing is running. Let's go ahead and connect that. So right away now there is a difference. The motor is wanting to start turning, and without grid assistance it'll only reach a certain point and then kind of stop. It's running off of the start capacitor basically, and it doesn't have enough RPM to engage itself to go into the full RPM. So again, we'll just use the grid momentarily for a second and get ourselves some power. So I'll adjust here now our voltage down here so we can see it on the scope. And that's what it looks like just connected there and just operating on its own. Let me get the math a little smaller so we can see it all on the display here, because that was going out of the display. And as you see, we have 13 volts now across our coil, so that's why it wants to kind of start turning. So let's, I'll do my momentary contact here, and I'll give you a scope view of what is going to go on when I start it. So there you go, it's now started, and we have 93 volts now across our motor coil. So we're getting closer to the ideal operating voltage, which would be 120 volts, and it's now turning. and it has quite a bit more torque. Normally if I would do that on the 120 volts, I would actually stop it. So this is what the new data looks like now, and quite surprisingly the results are very very good. And now you can see that we're returning 50 watts to the grid under these conditions. And you can obviously see we're out of phase, completely 90 degrees out of phase. And you can see how far down our return is. And if you look at what's going in and what's going back out is higher, and that's why we have less watts being used. But that's the condition that we do want, because basically we saw that when we load our shaft here, we are going to start reversing the ideal condition. So let me put my finger on the shaft here. So my finger's applied like it was in the previous at 120 volts, but we are still in a favorable condition now. Now I'll apply about double the amount of pressure, and still we're not using any power. Triple the amount of pressure, and still quadruple. My fingers get too hot. Okay, so I can't keep my finger on there, keep pressing more and more. But I think you're getting the idea that basically you have much more power at the shaft by doubling your voltage. And it is just like our previous tutorial when we had our 10 ohm resistor at 120 volts. We were able to get it to dissipate 30 watts, and just by doubling our voltage, it tripled. It went up to 90 watts of power dissipation. So for an induction motor, again, you want to use a low voltage induction motor. So this is a 120 volt one, and you want to use power, a high voltage power of a low impedance as well, a low impedance source. So unfortunately I cannot connect this to my alternator here because it is 110 volts, and there'd be no benefits. It'd be the same thing as what you just saw previously. But I think you might be now getting the idea that if your alternator is capable of outputting a minimum of 250 volts, now your 110 volt or 120 volt induction motor will be tripling the amount of work, if not more, than it can do. It'll vary from motor to motor. That is the direction that you want to go. And if you think about it, the Valley device, the generator that displayed its being self-looped, and I believe it did function, I'm quite sure it functioned under this principle, because it had a very low impedance alternator, which was a permanent magnet alternator, and it was actually a three-phase 600 volts, I believe, alternator. It was much higher anyways than 250. It was maybe in the 400 or 500 up to about 600 volts. So ideally the higher your voltage is of your alternator, and the lower RPM your alternator is capable of operating at that voltage, or obtaining that voltage, which would mean alternators that are designed for diesel engines, which operate at 1200, 1500 RPM. Once you reach that RPM, then you're actually outputting already its full voltage output. And that's most likely what he had on his device, a alternator that is designed for diesel engines. And it was a 10 kilowatt, and you know, one of the phases that he would have had from the alternator would be hooked up to the induction motor with basically just a series cap in between. And basically, as you see now, you can operate it off of reactive power, and you're not going to drain anything out of your alternator. And in fact, you'll be sending power back, like it is right now, to your alternator until this becomes under load. So that load would be represented by your other phase, which would be hooked up to some kind of circuit that you would be using power, like a resistive load, and that will reflect back to this prime mover and doing what it is doing there now, using those amount of watts and then transferring them to the load. So here we have a potential of about 50 watts that we would be able to transfer to our alternator. So this minus 50 watts, if you would now put a 50 watt load on the alternator, would turn out to be equal. So this wouldn't be requiring any power from the alternator, and now you'd be able to transfer it to your load. So I hope you are getting to understand how this works, and hoping that this will be informative for you. So your goal is highest voltage possible on your alternator, and minimum is 250 volts. And if you cannot work a 250 volt alternator and operate a 250 volt induction motor, you're now going the wrong direction. You would need an induction motor that's made for 120 volts, and you would need at least an alternator that outputs 220 volts to possibly loop the system. And ideally, like I say, the higher the better, and the lower RPM your alternator will be able to achieve its maximum voltage will be also a benefit, I'm quite sure. And those are all the characteristics that the Valley device had. And I guess that's about all I can give you, and I think I've given you enough that it should be a no-brainer how to go about and do this. So thanks for watching, and all the best in your replications of this interesting and worthwhile circuit. Bye now.